Assalamu alaikum everyone, I'm Amit Hasan Sadhin from the Faculty of Computing. Today I will present my final year project Road Defect Detection from Drone Images using Deep Learning Models. First of all, I am under the supervisions of Professor Siti Zaiton and I was co-supervised by Dr. Hussein Samma. I have divided this presentation into 8 sections: the introduction, problem statement, objective, scopes, previous findings, method, result, and discussions, and finally the conclusions. As you all know, roads are the lifelines of modernizations, connecting us to jobs, services, healthcare, and education. To keep roads safe and functional, maintenance is crucial. Defects like cracks and potholes are common road issues that require inspection. But due to the lengthy inspection time, the authorities are not always able to maintain the road timely as well as in a cost-effective way. Luckily, drones have revolutionized this process, saving time and money. With drones, we can efficiently maintain roads, ensure the safety and connectivity for all. Recently, deep learning algorithms have shown significant improvement in object detections, particularly the outstanding performance of YOLO family networks in this field. This research will show the competitive analysis of the latest YOLO algorithms performance with a newly collected dataset to detect the road defects. As for problem statement, only in Malaysia from 2015 to 2020, each year the number of accidents was more than 500,000, which has taken away loss of life and impacted the country's economy. And a massive percentage of these accidents are due to road defects. Traditional methods are insufficient to address problems of road defects detections while it's a matter of public safety and global economic development. In terms of making the road maintenance faster and efficient, road inspection systems is necessary, and it is essential to find a suitable algorithm. This algorithm should possess the ability to accurately identify and analyze cracks, potholes, and other road damages. Now, about the research objectives. This research aims to fulfill 4 main objectives. First of all, to find suitable YOLO-based deep learning models for road defect detections, to design a new image dataset based on road defect detections collected by drones, to compare the performance of various YOLO versions, namely YOLO B5S, M, L, X, and YOLO B7 for road defect detections, and finally, to compare among the YOLO versions and state-of-the-art technologies performance. Now about the scope of this research. This research unfolds a panorama of possibility. Firstly, we will explore into various YOLO family networks including YOLO B5S, M, L, X, and YOLO B7. Secondly, we will evaluate drone captured images of road defects. We will employ tools like PyTorch, Google Collaboratory, and Jupyter Notebook for model training and testing. Finally, the entire project will harness the power of Python. Previous studies reveal that annual sum exceeding $400 million is spent for road maintenance. Interestingly, a significant portion of this budget is directed towards road inspection, highlighting its critical role in maintaining our infrastructure. Different researchers are using unique strategy to speed up the inspection process with the help of various deep learning models. For instance, Parallel study used CNN to spot road defects. Among all deep learning models, YOLO stands out for its promising result. For instance, Mendel used YOLO version 2, a method that includes a 3x3 kernel and a max pooling with a 2x2 convolutional layer, and achieved an impressive F1 score of 87%. On the other hand, researcher Liu found that YOLO B5 provides high accuracy, making it a reliable choice for road inspections. Mass experiment shows that high accuracy, which makes YOLO a perfect candidate to evaluate with drone images. Now, in the methodology section, this is the entire research workflow for from literature review to result evaluations. YOLO B5, a single-stage object detector, is organized into 3 crucial elements: the backbone, neck, and head. So these integral parts allow it to transform traditional single-stage object detection to a more manageable regression model. In comparison with other versions, YOLO B5 shows impressive results due to its uses of CSP darknet, a network backbone that faster than others. Plus, YOLO B5 stands out for its adaptability. Instead of using the same model for all data types, it's adjusted to different dataset sizes with YOLO B5 V5S for small, Yellow V5 medium, large, and extra large set, thus optimizing its effectiveness and precision. This is the graphical overview of each Yellow V5 layer. Here is a detailed architectural walkthrough of Yellow V5. First, the backbone element pulls out meaningful details from input images. Next, the details are expanded into feature pyramid by the neck component. Following that, head section handle class probability and bounding box confidence. In the final step, Yellow V5 identify object frames with frames them within bounding boxes and present confidence score for each detections. This is the further details overview of used Yellow V5 architecture based on three main parts of the Yellow V5. The second algorithm used here is Yellow V7. One key difference between Yellow V5 and Yellow V7 is that Yellow V7 includes an efficient layer aggregations network, or ELAN. This forms the basis of Yellow V7 design, handling the efficient creations of network by managing gradient path, which allow for deeper network convergence and successful learning. The architecture also employs convolutional layer, or CBS module. This is a core part of Yellow V7 backbone and forms the ELAN, typically containing 4 CBS layers actually. So additionally, Yellow V7 utilizes an enhanced max pooling layer consisting of several CBS layers. So this layer is used for downsampling within a Yellow V7 architecture, further boosting its efficiency and effectiveness. Here is a more detailed view of Yellow V7 architecture, which is grounded in the efficient layer aggregations network, or ELAN. It is divided into three major components, each playing a significant role in the functionality of Yellow V7. For this particular study, I have gathered a set of 1000 images using drone. I have organized this image into distinct categories for training, testing, and validations. Now, when it comes to evaluating result, I have considered several key metrics: recall precisions, the F1 score, accuracy, and mean average precisions, or MAP. Now, in the result and discussion section, at first, this is a simple snapshot for use Colab and Jupyter Notebook. Here are some example images from the data I have used for training. From each model training, I selected two different images, input size 460 by 460 and 640 by 640 pixels. My experience by experiments with 460 by 460 pixel images revealed that Yellow V7 deliver a mean average precision, or MAP score, of 66%, outperforming other models. Additionally, Yellow V7 demonstrated shorter average inference time compared to Yellow V5 models, specifically ML and X. When using these 6040 by 6040 pixel images, the results showed a notable improvement. Yellow V7 achieved a remarkable MAP score of 70% and an impressive F1 score of 68.3%, suppressing all other utilized Yellow models. Additionally, Yellow V7 demonstrated faster average inference time compared to the other models. The variations of result between Yellow V7 and Yellow V5 models on different inputs image size can be attributed to a few factors. Firstly, larger input image size capture more details, allowing the models to detect smaller object with higher accuracy. Secondly, difference in the architectural design and optimizations of Yellow V7 and Yellow V5 may influence their performance on various images size. So the experiments highlighting the importance of input size selection for optimal performance. Now, in the comparisons of the state-of-the-art experiment utilizing various datasets, both Yellow V5 and Yellow V7 models consistently outperform previous approaches in road defect detection. This observation underscores the significance of employing drone-based inspection system and utilizing drone images for improved accuracy and efficiency. So, the use of drone technology allows for capturing details and comprehensive images of road surface, enabling the models to detect defect with higher precision. Thus, the superior performance of Yellow V5 and V7 models in this experiment highlights the potential and effectiveness of drone-based inspection system for enhancing road defect detection capabilities, which will lead to better and faster inspection systems. This is some of the example of inference images as can be seen in model provided a high confidence of detecting defects in drone images. Now, in conclusion, this research achieved all the declared objective and fulfilled the purpose. This research utilized object detections algorithm to identify root defects from diverse root conditions images. Future work suggestions include expanding the training dataset with more varying conditions of defect types to enhance the model stability, accuracy, and diversity. The integrations of twin layer approach is also proposed, wherein the first layer perform defect detections and the second layer classify the detected defect based on the severity and maintenance requirement. This is all. Thank you so much.